Okay, so hello everyone. Well, in this video, I wanted to make an introduction into what is sensor and data analysis. Okay, so first, I think that it is important that we discuss why do we need sensors in the first place. Okay, so why do we need sensors in an electric motor in particular? No, we have discussed in previous videos or in previous classes that, well, we are interested in studying electric motors, no? But why do we need sensors to monitor the state of the electric motor? Well, in the first place, we typically use sensors in electric motors because we want to know, for example, the energy demand, or in other words, the current demand of the electric motor. Also, we are interested in knowing what is the speed of the motor or the position of the shaft in order to see or know if the motor is achieving the speed or the torque that we want to deliver. Okay. Also, we want to use sensors to prevent faults. For example, maybe we need to detect excessive currents. And well, an excessive current could be a cause of a short circuit in the electric motor. Also, you can have insufficient torque in the machine that can be a product of the misalignment or a mechanical failure in the machine. Or maybe we are producing overheating. And overheating is an important concern for us because if the temperature increases too much inside this type of machine, you can melt the insulation, but also you can produce the magnetization. Okay, and the magnetization is important because basically what we are doing when we are producing the magnetization, we are reducing the magnetic flux of the motor. Okay, so if you reduce the magnetic flux of the permanent magnets, you reduce the torque capability, as we discussed previously. So that is why we're interested in measuring the temperature, no, of these electrical machines. And here in this table, I place like a distribution of some of the causes of fault of electric motors. For example, you can have rotor failure, bearing failure, old age. You can have contaminants, single phasing, or open fuse in the electric motor. You can have miscellaneous losses like angle misalignment, offset, misalignment of shifts. But the most common cause of faults is the overloading. Okay, and overloading basically is related to the fact that we are demanding too much power from the motor, and we want to find a way to reduce that, okay, or prevent that. Okay. Also, well, I was discussing this previously. You can also produce the magnetization, no? Maybe you are demanding too much power to the motor, and that power is producing a lot of heat inside the machine. For example, for a permanent magnet synchronous motor, the main source heat is the windings of the motor. Okay, they are dissipating a lot of heat, and that heat can increase the temperature of the permanent magnets and produce the magnetization, and this reduces the torque capability of the machine. Okay, that is why we are interested in measuring or knowing the state of the motor. Okay, so well, the typical way to monitor the state of any electrical machine is by using sensors. Okay, and recall that a sensor is basically a device. No, in particular, it's an electronic device that produces a voltage or an electrical signal in response to a physical stimulus. Okay, and here I listed some types of sensors that you can use to monitor the state of any machine or any process. For example, one of the most common variables that we want to study are the temperature motors. Also, we have gas sensors, humidity sensors, potentiometers, and encoders. Okay, so what are the temperature sensors? Basically are devices that produce an electrical signals, typically a voltage, in response to changes in temperatures. And the most common types of sensors are the thermocouples and the thermistors. Okay, so what is a thermocouple? A thermocouple, I will be using this diagram as a reference, is basically having a junction of two different metallic objects. For example, here we have chromol and alumel. And well, we are forming a junction of these two metallic objects. And when you apply heat to this junction, in the other side, you can produce a voltage, okay? Or you are inducing a voltage in the other side, okay? And this effect, no, when you are placing two junctions of metallic objects and then you apply heat, is called the Seebeck effect. And well, this is an animation that illustrates a little bit about what is happening in the Seebeck effect. We have again two metallic objects, okay? And when you apply heat to the junction of these two metallic objects, you will produce a current flow, okay? And this current flow or this movement of electrons produces a voltage that we can use to estimate the temperature. And this is an illustration of a thermocouple. Another type of temperature sensors are the thermistors. And the thermistors are basically electrical resistance, okay? But contrary to thermocouples, what the thermistor is doing is that it is changing its resistance in accordance to the change in temperature. And you can have different presentations. You can have a negative temperature coefficient thermistor or a positive temperature coefficient thermistor. Okay, there are two types of thermistors. And this is a diagram of the behavior of the thermistor. For example, for the negative temperature thermistor, when you're increasing the temperature, you're reducing the resistance. And on the other hand, for the positive temperature coefficient thermistor, when you're increasing the temperature, you are increasing the resistance. Also notice that, well, there is a problem with the thermistors is that the relationship between temperature and resistance, it is not linear. And that is a problem because you need to calibrate the sensor. You need to find like a coefficient, find the coefficient in order to correlate the resistance with the temperature changes. But making this calibration is a little bit tedious or challenging. That is why many people use another type of sensor that is called the LM35. This is the a photo of the sensor. It is very typical. You can buy one of these, for example, in Steren. But the important fact here is that, well, you have three terminals. You have the ground terminal. This is the voltage source terminal, and this is the output voltage of the thermistor. Um, but the advantage is that it is very easy to use. You only need to connect it and that's it. Also, it has a very low power consumption and you can power the device with 5 volts. You can use your computer to turn on this thing. And also the current consumption is of 60 microamperes. So it is relatively small. Also, well, it produces an analog output. We will discuss later what is an analog output. We are referring here to analog signal, and the analog signal is basically an electrical signal that has continuous values, okay, across time. And also, one of the disadvantages is that the relationship between temperature and the voltage is linear, okay? In fact, for every increase or every degree of temperature, you will have an increase of 20 millivolts in the electrical signal. So it is very easy to correlate the temperature with the voltage changes. And well, this is all for the temperature sensors. Now I want to discuss what is the gas sensor. So the gas sensor is basically a model. In particular, this model of gas sensor is the MQ5. And well, according to the manufacturer, you can detect many types of gases like a liquefied petroleum gas, natural gas, hydrogen, and coal gas. But well, I do not recommend this type of sensors if I am true with you. Okay, this is a model that you can connect very easily with an Arduino. And well, they tell you that they use this sensor in industry. But the problem is that it is very complicated to calibrate. But I think that, well, you can use the sensor if you only want to detect, no? If you want to detect one of these gases. But if you want to measure the gas concentration with this sensor, it is a mess. Okay, it is a completely mess. Some years ago, I tried to use this sensor in order to detect alcohol. and it was a mess. No, I was in the chemistry laboratory like 2 weeks, and also I was working with the technician of the laboratory because, well, I believe that he was more expert than I. But well, it was really a mess. No, it was real difficult to calibrate the sensor. Here I was showing you um what is the air concentration, what is the H2 concentration according to the change of resistance. Okay, the sensor basically what it's doing is that when we have the presence of one of these sensors, its resistance is changing. And according to this graph, you can correlate the change of resistance with the gas concentration in particles per million. But the problem is that, well, in fact, the relationship looks linear, but here they are using a logarithm scale. So the relationship is not linear. And also you can see that there are some gases like CO or alcohol that their curves look very similar, okay? So also you need to calibrate the sensor like in a vacuum situation, but having vacuum conditions is quite complicated. And also you know that gases are volatile, no? They want to occupy all the space that they want. So having that condition in a laboratory is quite complicated in order to only calibrate the sensor and try to fit a curve or maybe calibration for all the gases and know for which gases well, in order to know what is the gas concentration of each of these gases. Okay, so it is a mess. What I recommend to you, if you in some time of your life want to use a gas sensor for any project, is to search for a sensor that is specific for the gas that you want to estimate or detect their gas concentration. And here I place a table. You don't need to memorize this. But what I want to highlight is that, well, it is better that you use a sensor for the specific gas that you want to use. And here I place some of their key features and their applications. But this is only an overview. You don't need to worry about learning all of this. But just take in mind that if you want to, for some projects, you want to detect gas, it is better that you buy a sensor, okay, that can detect the particular gas that you want, okay, because it is a mess. It is a complete mess to do that. Okay. Well, another sensor, in fact, we'll be using the sensor later is the potentiometer. Also, they call them whippers. And the potentiometer is basically a variable resistance, okay? I can use or produce many resistance values by only moving a little bit this screw, okay? And well, there are different presentations. For example, you can have this one that is a 10 kilo ohms potentiometer. Basically, this means that I can produce resistance values between 0 kilo ohms to 10 kilo ohms. And also, we have another presentation in which you need a screwdriver in order to change the resistance. And also, well, these devices acts as voltage dividers, no? The way in which we can know the resistance is by measuring the voltage, but also you can use a voltmeter or a multimeter in order to measure the resistance of the device. Okay, and well, this is some of the symbology that you can use to identify the sensors. And well, these devices have a lot of applications. For example, you can use this variable resistance to change, for example, the volume in a guitar amplifier or in a stereo, no? They are typically used as faders in audio equipment. And also you can use them as dimmers, switches, or also to control the brightness in televisions. Okay. And well, another also we will be using these potentiometers as the input signal to control the speed and the direction of our electric motor. So what are the applications of potentiometers? Well, these are a list that you can consult. These are some of them. Well, and here we have another sensor that is called the encoder. And the encoder is the sensor that we use in order to monitor the angular position or the speed of an electric motor. And what is the encoder? It's basically a disk in which we have different holes around the perimeter. And we know how the number of holes that we have placed around the perimeter. And the idea is that we can use a light sensor in order to detect the presence or the absence of the hole. So we can use this infrared sensor in order to count the number of holes that we are detecting when the disc is moving, no, or when the motor is turning or spinning. And based on those pulses, we can count the number of holes that we are detecting while the motor is moving or is turning. And based on those number of pulses or the number of interruptions of this infrared light, we can measure the speed, okay? Because we can count how many pulses we have counted within 1 second or within 1 minute. And we can translate that into revolutions per minute or radians over second. Okay. And also there's other types of encoders that are called the quadrature encoder that basically consists of two disks. We have one outer circle and one inner circle, and the holes are misaligned by 90 degrees, more or less. And the idea is that, well, we want to produce two different signals. That is, we will be using two different infrared sensors. And based on those infrared sensors or the signals produced by those infrared sensors that are labeled as channel A and channel B, we can know what is the direction at which the motor is turning. Okay, so we want to produce two different signals that are called channels. And based on the phase difference between these two waveforms, we can know if the motor is moving counterclockwise or clockwise. Okay. So this is another type of sensor that you can encounter and is widely used. For example, we can apply a control engineering to this motor and control its velocity and speed. And we can apply a PID controller in order to control the speed of the motor, okay, by using this encoder. Okay. Well, this is a video that I want to play later for you in order to understand better what is the encoder. But now that we have discussed a little bit about the sensors that we can encounter in industry, some of them at least, my recommendation is that this is only an overview of the sensors because there are many. Uh, my recommendation is that when you want to select a sensor for any application, you always have available the datasheet. In fact, you need to make some research when selecting a particular sensor. And also, maybe you want to work in designing the sensor, and that's another stuff. But you always need to depend on the application, no? And based on that application, you can search or make a research related to which is the best sensor for your particular application. Also, you can you can call the manufacturer in order to tell you what is the best for your application or for your equipment. Okay, this is only an overview of some of the sensors that you can see, but I want to concentrate in another aspect that is typically overlooked. Okay, because you can have the sensor, but sometimes some people miss out that you also need to be careful about how you are pre-processing the signal before sending that information to a computer or to a data acquisition system, for example. You maybe need to use a microcontroller like an Arduino to collect the data, but the microcontroller needs the electrical signal in a particular format or in a particular presentation. Okay, and that is the whole idea of data acquisition. It's basically the process in which we need to preprocess the signal in order to pass the electrical signal into a microcontroller, and what are the steps that the microcontroller is taking in order to send the data to a computer, okay? And then we can analyze it, no, or perform certain statistical or data analysis techniques in order to make deep analysis of the information that we are collecting. And so the first step is to understand what is a signal. And previously we discussed that well, all of the sensors produce electrical signals that, well, are presented typically in the form of voltage. So the signal is basically the signal from the sensor, but measured across time, okay? For example, in this picture, I am showing you the data of a temperature sensor, okay? And in fact, this is one of the projects that we have worked on in the past. And this is data from the windings, okay? The temperature of the windings of a permanent magnet synchronous motor. So the signal is basically this measurement that we are taking from the sensor during a very long time. Okay, it can be 1 second, it can be 1 minute, but this is basically the signal, no? It's the measurement of the sensor across time that we are recording or that we are monitoring. And we have two different types of signals. We have analog and digital signals. So what is an analog signal? An analog signal is basically a signal that is changing their values across time, but its particular characteristic is that it can assume an infinite value of, well, it can assume infinite values or infinite values of voltage. For example, here we are showing you an analog signal that can take values from 0 to 5. Okay, in fact, this is the signal of a sinusoidal waveform. But the important thing is that, well, there are many values that the signal is taking between 0 and 5. Okay, there are more than two values or more than two levels that the signal can assume or can take. And also we can characterize analog signals in three components. First is the level, that is the level of voltage that the signal can take. Also the form or the shape of the waveform. For example, here we can see that this has the form of a sine wave, more or less. And also we can characterize the signal based on the frequency. Okay. And how can we know what is the frequency of the measurement? Well, we can use the Fourier transform. Okay, that is application of the Fourier transform that, well, we discussed with some of you in a previous module. In fact, the exam was focused on that, no, in researching what is the Fourier transform, no? What is the interpretation of that? In fact, another type of signal is the music, okay? The music is basically a sound. No, it's an electrical signal that we can measure during a very long time. Okay, and in fact, music is typically analyzed in the frequency domain or is characterized in the frequency domain. Well, in reality, music, well, this is only like a small deviation that I'm taking. You can analyze music in time and frequency simultaneously, and you use representation that is called the spectrogram. Okay, so this is a signal, no? In particular, an analog signal. It's a signal that can take more than two values and that can be characterized by levels of voltage, its shape, and the frequency. So now, what is the digital signal? Well, contrary to analog signals, digital signals can only take two values. Okay, for example, one of them, the typical digital signal is basically a square waveform in which we are moving from 0 and in this case to 5. But the signal can only take those values. Okay, that's why we call it digital because it can only take two values, 0 and 1. Okay. And well, we can characterize the digital signal by its state. For example, we can say that the 0 volts value is the off state and the 5 volts value is the on state. Okay, that's why we call it digital because it can assume binary values. Okay, and typically digital electronics works with digital or binary data. Okay, and also the rates, no? We can also characterize the digital signal by the transitions between the off state to the on state. And that is basically the rate at which the signal is moving from one state to another. Okay, but the difference or the main difference compared to analog signals is that digital signals can only take two values. Okay, and analog signals can take more than two values. Okay, and we can characterize them better by their shape or their frequency domain content. Okay, also, I wanted to mention that also we can say that the digital signals have two levels. We refer previously to the off and on state. Also, we call the off state as the low level voltage, and the on state, we call it the high level voltage. Okay, so now that we know what is a signal, and now we can discuss what is the signal conditioning. And the signal conditioning is essentially preprocessing the information of the sensor or the signal before we transfer the information to a microcontroller like an Arduino. Okay, but why we need signal conditioning? Well, when you're acquiring data from a sensor, you always are susceptible to electromagnetic noise. Okay, any sensor is susceptible to some interference. Okay, and we call that interference the noise or the electrical noise that is present in the data that we are collecting from the sensor. Okay, and we want to remove this noise. For example, if you compare this sinusoidal with this one, you can see that the signal source is clean, but when the sensor, since it is influenced by electromagnetic interference, you can see that we have a lot of variations in the signal, and that is a problem. Okay, also, and this happens a lot, for example, with biomedical signals, when you want to measure, for example, the electrocardiogram with an electrical signal, well, that is a mess, okay? Because, well, you need to place electrodes, but the electrical signal is very small. It has a very small amplitude. And maybe, for example, these signals have around 20 millivolts. So the signal is relatively small, and you need to amplify that. Okay, and in order to do that, to amplify the level of voltage of the signal, you need to use a device that is called the operational amplifier. Okay, and for example, if you have used these sensors that are these cells that allow you to measure the load or the stress in an object, well, they are also susceptible to noise. Okay, and also you can use some filtering to remove the noise, but also amplify the signal. Okay, so once you have cleaned or amplified your signal, you can translate to another circuit that is called the analog to digital converter. Basically, the idea is to take the signal and transfer the voltage levels into a discrete representation, okay? And once we have those values into a discrete representation, we can convert them to a binary format in order to make a software that can store or we can make a program based on the data that we are collecting. And the key step before converting the analogs to digital conversion of the signal is to use a sampling frequency, okay? So we need to take data from this signal in a certain time interval, okay? In fact, there is a theorem that helps us to know what is the frequency at which we should take in those samples in order to correctly capture the dynamics of the sensor that we want to use, okay? So, well, first I want to discuss what is the process of signal conditioning, and then I will talk about what is the analog to digital converter, okay? So as I told you previously, one of the things that we want to make is to amplify the signal. So to do that, we need to use an electronic device that is called the operational amplifier. And the operational amplifier has the following circuit, okay, or the following representation. Basically, it's like a triangle in which you have two input terminals. We have a positive input terminal and a negative input terminal. This is where the input signal or the input from the sensor can enter, okay, the circuit. Also, we have two terminals that are called either VCC or VDD or VEE or VSS. And these terminals are used to power the device. In fact, the operational amplifier, in order to be powered, needs two types of sources. Okay, we need a positive voltage source and a negative voltage source of the same level in order to power the device correctly. And then we have an output voltage pin. Okay, so here the input signal is centering, and we can measure the output voltage and we can see the effect of the operational amplifier because the operational amplifier can perform many operations. Maybe we can add different signals, we can subtract different signals, we can even integrate or compute the derivative of the signal using this device. Or, well, you can see the effect of the amplification or the attenuation of the input signal, okay? And also you can generate filters. In particular, if you design an electronic filter to remove the noise, it's called an active filter, okay? And this is an schematic or a photo of the operational amplifier. This is one of the most common ones, that is the 741. And here I'm showing you the schematic of this electronic component. Typically, this device have 4 pins. But the important part here is that you notice that, well, the schematic tells you about the connections, okay? There is a relationship between this triangle and the connections that you are seeing here. For example, 7 and 4 are basically the pins in which you need to power the device. Also, terminals 2 and 3 are the positive and negative input voltages of the operational amplifier. Pin number 6 is where we are measuring, or we can detect the output voltage. And no, pin number 8, you don't need to connect that. That's why we have this NC that is not connected. And input 1 and input 5 are pins to place or to add certain offset to the input voltage. Okay? This is another representation. And well, this is one of the typical configurations. In fact, this is called the inverting amplifier. And you can use this inverting amplifier to amplify the voltage level of your input signal, but also change its or invert its amplitude. Okay? You can convert the positive cycle to negative or the negative cycle to positive. But at the same time, you can amplify the signal. So, well, you can use this operational amplifier in different configurations. For example, you can work with the non-inverting amplifier. And what is the characteristic that, well, you need to connect your input signal or your sensor to the positive terminal, and then you need to connect to ground a resistor labeled as R1, and R1 is connected to the negative terminal. And we have what we call a feedback resistor that is connected between the output voltage and the negative terminal that is labeled as R2. So the idea is that you can place this configuration and then connect the resistor in this form. And well, there is a characteristic that we can amplify the output voltage and the input voltage and see that effect in the output voltage based on the value of these two resistors. This GB refers to the gain of the operational amplifier, but basically relates the output voltage and the input voltage. In fact, this will be the transfer function of the operational amplifier. But let's say that if you place a value for R1 equal to 1 and a value of R2 equal to 1, and you divide this by 1, you will obtain a value of 2. Okay? So this means that the output voltage is equal to 2 times the input voltage. So this means that you are multiplying or amplifying the input voltage by a factor of 2. Okay? And that's why we call it the non-inverting amplifier, because also the amplitude or the of the signal stays the same. Okay. But in the inverting amplifier, the behavior is a little bit different because, well, this gain again refers to the relationship between the output and the input voltage. Okay. But you can also amplify your output signal according to the input signal by the relationship between R2 and R1. So for example, if I use R2 equal to 2 and R1 equal to 1, I will be amplifying the signal by 2, similar to the previous case. But since this is an inverting amplifier, we need to take into account a negative sign, okay, in order to see or to consider the effect of this inverting amplifier. In fact, you can see that compared to the previous case, the input voltage is connected to the negative terminal through the R1 resistor. Okay, And in the previous case, the input voltage was connected to the positive terminal, okay? So this is another configuration that you can use to amplify a signal. And also we have another one that is called the voltage follower. This is also called a buffer. And the idea, as you can see that here we are not using any resistor and that the input voltage is connected to the positive terminal. The use of this configuration is to ensure that we are capturing the information or the signal from the sensor correctly. And why we're using this configuration? Well, the reason is that operational amplifiers at their input have a very high impedance. So having a very high impedance translates with having a very high voltage drop. Okay, so by using these configurations, we can ensure that thanks to the high impedance of the operational amplifier, we are dropping all the voltage from the sensor into this device, and the operational amplifier can transfer that drop of voltage very smoothly or very easily to the next stage, because the next stage has a very low impedance, okay, at the output. So that is useful. In fact, many microcontrollers use this buffer in order to capture correctly the signals that are sent to them. Okay. In fact, many analog to digital converters have a buffer in their design in order to ensure that they can have a very good voltage drop in their inputs in order to read information correctly. Okay. So this is the three configurations of operational amplifiers that you can use. And well, here I am showing you an example that, well, a simulation that I made in Tina. For example, this is the simulation of a non-inverting amplifier. You can see that I set the value of R1 and R2 equal to 1. So that means that my signal should be amplified by 2, according to the expression that I place here. And well, this is the results of the simulation. You can see that when I place at the input, that is the green signal, as a cosine function with an amplitude of 1, well, the output voltage is amplified by a factor of 2. You can see how the amplitude reaches the value of 2. Remember that the output voltage, according to this figure, is like the brown or between brown or red signal, okay? And also you can generate an inverting amplifier by, well, again, using this configuration of the operational amplifier. And again, well, you can see that I set the value of R2 equal to 2 and the value of R1 equal to 1. So that means that my output voltage will be amplified by a factor in 2, but also the amplitude will be inverted, okay? So you can see here that, well, the amplitude is inverting, but also it is amplified at the same time. Okay, so this is one of the parts of signal conditioning, okay? In which we want to amplify the data collected from the sensor. But, well, there are other instances in which, well, the sensor can have interference in its measurement, no? Or in its data. And that interference is called noise. So sometimes the signal that you are acquiring has two components, no? In simple terms, you have the signal and you have noise, and they are added together, or they are superposed with each other, okay? In fact, this addition is a consequence of the superposition principle that we discussed a little bit in the circuit class, okay? Basically, the final signal is the result of adding them together. But you can see here that when you consider the noise or you have noise in your data, the output signal or the signal that you are measuring is deformed a lot, okay? There is a lot of differences when you are analyzing the pure signal and the signal with noise. And that is why we are interested in filtering or removing this noise. And well, how can we know in which frequency band the noise is present? And what you can do is to apply the frequency, well, sorry, the Fourier transform to your signal with noise. Because if you apply the Fourier transform to your signal with noise, you can obtain a frequency spectrum, okay? And based on that frequency spectrum, you can determine, based on the amplitude of that frequency spectrum, in which frequency bands the signal is contained and which frequency bands contain noise, okay? And that is useful because if you know in which frequency bands you have the noise, you can filter the noise according to the frequency domain, okay? That's why we needed to study Fourier, because if you can characterize the frequency content of your measurement, you can very easily design electronic filters that remove that noise, okay? And well, in order to understand the typical way in which we design electronic filters that can be either analog or digital is to use a graph that is called the Bode plot. And the Bode plot is basically expressing the behavior of a transfer function in the frequency domain. And here at the right, I place a picture of a Bode diagram. Here you can see in the y-axis the magnitude that is expressed in decibels. In fact, you can convert the magnitude to decibels by using the expression that I place here. You need to take the base 10 logarithm of the output voltage of your system divided by the input voltage, and then you multiply this result by 20. But here you notice that we are relating the output with the input voltage. In an electronic filter, this output voltage will be your signal without noise or without certain frequency components. And the input voltage will be the signal that we're measuring directly from the sensor. So here we are using this Bode diagram in order to know what is the frequency response of your circuit or your electronic filter, okay? So if you analyze this Bode diagram, we have placed in the x-axis the frequencies, okay, all the possible frequencies. And in the y-axis, we have this magnitude that is the relationship between the output and the input. But you can notice that between the 1 and 10 values of frequency that can be hertz, for example, you have magnitude in decibels that is equal to 0. So when you have a magnitude in decibels that is equal to 0, that means that the relationship between output and input is the same. Or in other words, the output voltage has the same amplitude as the input voltage. That is that for this range of frequencies, the output and the input voltage will have the same amplitude. But as you increase in frequency, you will notice that the frequency of the signal starts to be attenuated, okay? How do we know that? Because the decibels start to decrease. So this means that the relationship between the output and the input voltage gets lower. In other words, the amplitude of the output voltage is lower, okay? In this region, the amplitude of the output voltage is lower compared to the input voltage, okay? That's why we have negative decibels. In other words, this means that for frequencies greater than 100, the signal would be attenuated. In other words, we are filtering the information that is contained in that frequency region, okay? And based on that, we can design filters because if we know that the noise is present around this region, we can design an electronic filter that can attenuate or reduce that information. Also, we have another plot in the Bode diagram that is the phase plot. And the phase plot basically tells us what is the phase difference between the output and the input voltage. Okay, so if you analyze this phase diagram, you can see that as you increase in frequency, well, there will be different phase shifts between the output and the input. That means that there is like a delay of the output voltage compared to the input voltage. Okay, there is a phase difference. Okay, maybe the output voltage is lagging the input voltage. But in order to know that, we need to look into this phase diagram. Okay, but basically what it's doing is to tell us about what is the phase difference or what is the displacement of the output voltage compared to the input voltage. Okay, and this is correlated to what we discussed in the AC circuit class related to leading and lagging. Okay, this phase difference is telling us about this um, uh, difference in phase between the two signals. Okay. Okay. So, well, you can have many filter types. For example, you can design low pass filter. Basically means that all the frequencies below a certain threshold that we label this threshold as the cutoff frequency will pass the circuit or will pass to the next stage, and all the frequencies above a certain threshold will be attenuated, and we call this region the stop band. Also, you can have high pass filters in which all the frequencies that are above certain threshold will pass or will have the same amplitude when we compare the output and the input voltage. But there are other frequencies that will be attenuated when they are lower compared to the threshold. Okay. Also, we have a bandpass filter that is essentially a filter that only passes certain frequency band. In fact, we can produce a bandpass filter by combining a low pass and high pass filter. It's basically the combination of both. And also we have the notch filter. And the notch filter intends to attenuate the information contained in a particular frequency or in a particular frequency region. Okay. Also notice that, well, it is impossible to have ideal filters because you can see here that there is like a certain decay over time. But sometimes we want to have this abrupt change, okay, in which we are correctly attenuating the information very precisely. But in reality, we cannot do that, no, because filters are not ideal, okay? They have certain decay over time when we analyze them in frequency. And also that is related to the problem that the Fourier transform cannot be applied to discontinuous signals, okay? Because you can see here, if you analyze this square, that we are jumping very abruptly between a certain point to 0 decibels, okay? But Fourier doesn't like that, okay? So that's why we have like these transitions. Okay, so there is another thing to consider. No, you cannot have, or it is impossible, at least with the theory or the signal processing theory that we have, to produce these abrupt changes. Okay, that's why we have like this decay in the filtering design. Okay, so how can you design these filters? Well, the most simple way is to use passive components. Passive components are like resistors and capacitors, or maybe inductors. For example, if you place a resistor and then, well, you have your input voltage, you have a resistor, and the output voltage, if you measure it in accordance to the capacitor, you will produce a low pass filter. And you can define the threshold at which the low pass filter is allowing to pass certain frequencies by using the following formula, that is 1 over 2 pi times RC. Okay, and with this value, you can define the threshold of your low pass filter. Also, you can generate a high pass filter, again, by using the same components, but now you are measuring the output voltage according to the resistor value. Okay, but again, you can determine the threshold of your high pass filter using this equation. Okay, so that is another aspect to consider. And well, in fact, um, we can reproduce this body diagram. Remember that we say that the body diagram is like plotting the transfer function. So what we can do is to compute the transfer function of this RC circuit. For example, for the high-pass filter, you will obtain this transfer function, and for the low-pass filter, you will obtain this transfer function, okay? But remember that the transfer function is a S-domain representation of any system. So we know that here in S, we have a consider the frequency, no? It is embedded in that. So, well, let me write it right here, no, in order to be clear. We know that S is equal to sigma plus J omega. In fact, well, the final exam was related to this idea, not that you make a small research related to what is the frequency and the Fourier transform. But the reason of that, or the reason I placed that homework in the first place, it was for you to study a little bit about this concept. Okay, but since here we are interested in the frequency response of the system or the circuit, we can say that S is equal to 0, okay? So S will be equal to J omega because we are not interested in the transitions, we are interested in the frequency behavior of the system. So if we do that, you will obtain at the top, for example, for this J omega, and this is divided by J omega plus 1 over RC. Okay? So what we can do is to say, okay, I can place a value of the resistor as I want and a value of the capacitor as I want. And I will have a function that depends on frequency. So what I can do to simulate or to generate this body diagram is to plot the behavior of this transfer function by changing the values of omega between 0 and infinity. Okay? And I can do the same for the transfer function in this side. Okay? So, well, that is the idea, no? That's why we study a lot this transfer function. And that's why in the exam I placed this circuit. Because at the end, what you were analyzing, okay, was a filter, okay, an electronic filter. And we can understand this electronic filter in the frequency domain. Okay, and by knowing that S is equal to sigma plus J omega, we can say, okay, I want that S is equal to 0 because I am not interested in the transition behavior of the system. I want to focus on the frequency domain behavior, but that is basically a Fourier transform. Okay, we are basically analyzing the frequency domain behavior of these RC circuits. And it's quite interesting because also you can use this representation to generate digital filters. And what is a digital filter? It's basically an equation that we can program in the computer, okay? We can program this filter in the computer and we will see this behavior. And that is interesting because instead of using electronic components, you can use programming to filter the information. But, well, that is a topic that requires further discussion because it's related to another transform, okay? We have discussed about Fourier transform, Laplace transform, and in order to program this digitally, we need to use another transform that is called the C transform, okay? But that's another topic. In fact, I only telling you this only to for you to have like an overview, but that's another topic, no? Uh, that requires its own merit because well, I didn't see digital filters in the career, but I can tell you that that's another topic, okay? You don't need to worry about that. In fact, it's quite similar to the Laplace transform. Now it's like a discrete form of the Laplace transform. But just take into account for this class that you can produce filters in order to remove noise by considering the resistor and the capacitor. Okay? So, well, let's continue. Well, here I make an example. I design a low-pass filter with a cutoff frequency of 2 Hertz. Remember that this cutoff frequency is the threshold at which the frequencies will be either attenuated or maintained the same. So since it is a low pass filter, this means that it is allowing to pass as they are frequencies that are below 2 hertz. In fact, I place this cursor in order to show you that, well, this is basically or approximately the value of 2 hertz. And we can see that there is a decay at the curve frequency of -3 decibels. That is a characteristic of these filters, that at the cutoff frequency, you will have a decay of -3 decibels. And well, you can see, or we can use TINA to produce this Bode plot. Okay, that is basically the frequency response of the system. Okay, this is the input voltage and this is the output voltage. So TINA is automatically computing this behavior. And also notice that we have this phase shift. So as an example, well, I introduced to this circuit a cosine function with an amplitude of 1. But I simulate that the input sinusoidal has a frequency of 10 hertz. But since the signal has a frequency of 10 hertz, we will expect that the signal is attenuated to some degree. And well, you can see here that the output voltage, that is this BF1, has been reduced, okay, compared to the input voltage. So we can see that the filter is having it's having the expected behavior. And here I place a input cosine function that has a frequency lower than lower than 1. Okay, sorry, lower than 2. And you can see here that the amplitude stays mostly the same. Okay, if you compare the input and the output voltage. Okay, so you can see here that also you need to be very careful when you're filtering, because also you can reduce the amplitude of your sensor. So you are in a sense losing some information. So that is why you need to design your filter very effectively in order to avoid this information loss. Okay. And also here I design a high pass filter. I basically do the same. Only I change the circuit, but the current frequency is the same. Okay, and again, you can see that we have these transitions between the stop band and the pass band, and below is the phase diagram or the phase plot. Well, so this is an example, no, how you can work with a high pass filter and a low pass filter. But now we have completed the signal conditioning. No, we have amplified and we have filtered the signal. But now we need to perform another task. That is, okay, now I want to collect the data with a data acquisition card. Okay, so how can we do that? Well, all of the data acquisition cards has an electronic circuit embedded that is called the analog to digital converter. Basically, the analog to digital converter is taking the input signal and is taking samples of the input signal at a particular time interval. And we call that time interval the sampling frequency. Okay. So at the end, we are using this process because computers cannot take measurements instantly. Okay. They can be very fast, no? But they cannot compute or take samples at the smallest amount of time possible. Okay. So what we need to define is a sampling frequency. That is the rate at which we are taking the measurements from the sensor. And we are basically producing a discrete representation of the original signal. But you need to be careful about this, okay? This is another example. You can see that we are taking samples during certain interval. No, for example, you can see here that we are taking samples every 0.05 seconds. Okay, so we are basically discretizing the continuous values of the analog signal, and we are having this discrete output. Okay, in fact, well, you can see here that, well, we are calling digital because now we are working with digital values. Okay, but the reason for that is that we cannot measure all the smallest amount of time possible. The computer cannot do that, no matter how fast they are. In fact, you need particular processors to collect data effectively, and we call that real-time processors. A real-time processor is basically a computer, no, to put it in a way, that can take samples in a deterministic fashion. That is, if I program the device to take samples from the sensor every second, it will always obey that and it will always take one sample always at 1 second. But you cannot use, for example, use computer to take samples from a sensor because this computer is not real time. Okay? And why is that? For example, you can program in MATLAB a line of code in order to measure the execution time. But if you measure the execution time one time and then you measure it again, you will notice that the execution time that you're measuring is always different. And the reason for that is that the processors that our computers use are not real time. Okay? And real time is not about the fastest processor. It's about taking or executing code always at a deterministic time. Okay? We always want to take data in a deterministic behavior because that ensures that we are correctly sampling all the important dynamics of the sensor. Okay, we cannot take samples arbitrarily. Okay, that will be a problem and you will obtain very strange dynamics. Okay, and well, there is a rule, no, there is a theorem that is called the sampling theorem. Okay, that basically states that if you want to capture all the information from your signal correctly, you need to sample with your computer at a sampling frequency that is at least 2 times higher than the maximum frequency of your signal. So let's analyze this in this picture. Let's say that this sinusoidal has a frequency of 1 hertz, okay? So that means that the signal repeats itself, no? It goes from this point to this point every second, okay? So imagine that I am sampling this signal at 1 second. So I will be capturing this point, then I will capture this point, and I will capture this point, and then I will capture this point again. So when I have this data in my computers, and I try to make some interpolation, I will get a line, okay? But that is very different from the signal that I have. That's why I need to sample higher than the maximum frequency of my signal. So the recommendation is to use the double of that frequency. That is, instead of sampling at 1 hertz, I want to sample at 2 hertz, okay? So if I sample at 2 hertz, that if I translate this to time, this will be equal to 0.5 seconds. So if I take as an example again this signal, well, I will be capturing the signal at this point, and then I will capture the signal at half a second, no? That will be this point, and then I will have this point, and then I will have this point, and then I will have this point, and so on. And now you can see that when I make some interpolation between these points, well, I will have a signal that is quite similar to the sinusoidal that I have. But you can see that this is not okay because it looks like a triangle. That's why we need to sample at least higher than the maximum frequency of my signal. Okay, so what I can do is to take more samples. Typically, many computers or data acquisition systems oversample the information, okay, in order to have a better reconstruction of the signal, okay? So, rule, no? A rule of finger, to put it in a way, is to sample at least 10 times higher than the maximum frequency of the signal in order to ensure that you have a good interpolation of the dynamics that you want to capture, okay? But there is a doom rule, okay? It's not a reality, it's more like trial and error and see if you are reconstructing a little bit better your information, okay? So, and also let's talk about, no, I want to show you this video that explains, or at least you can visualize what is the importance of the sampling frequency. And I want to be very, how can I put it? I want to put this information to you or explain to you to the best I can this because many people forget about this. Many people, okay, I will collect data, I will measure the data, but they forget about this. So when they are making their analysis, maybe they are getting good results, but maybe the dynamics that they're capturing are very random. Okay, so this is very important. It's not about velocity, it's or to the best you can, it's about having or reduce the biases in your analysis. Okay, and let's make it, well, I will show you this video. What they are doing here, now I will explain the setup. They have a speaker, okay? And they connected the speaker to a computer that is playing sounds at a particular frequency. So the speaker is vibrating at the frequency of the sound. And they connected a hose, okay, to this speaker that is in which they are introducing or water is flowing, okay? And they are capturing the flow of the water with a camera that is sampling at 20 frames per second. That can be translated to 24 hertz. But you can see here that when they are sampling um, at 20 hertz and the sound that they are playing is at 20 hertz, it seems that the water is static, that is not moving. But we know that from a physical point of view, that is not possible, no? The water should be flowing from the hose to the ground. And also you can see here that when they are placing an audio frequency of 20 hertz, but the camera is sampling at 24 hertz, it seems that the water is going from the ground to the hose. And that is not possible, no? It's not physical possible because it seems that the water is overcoming, no? The gravity of the earth, no? So it's quite strange. So that is the relevance of correctly setting your sampling frequency because you will not obtain the dynamics that you're expecting. And maybe the information that you're capturing with your sensor is wrong, no? It is biased. Okay. So one final step that you need to take into account is the problem of quantization and encoding. Okay, so quantization is basically the process of mapping a continuous infinite value to a smaller set of discrete values. That is basically the process that the ADC is performing. No, we are transferring these continuous values to a discrete representation. Okay, and encoding means converting the sample data point to a binary representation. Okay, so, well, quantization is performed by the ADC as follows. Basically, we need to take into account the resolution of the ADC. For example, many analog to digital converters have a bit resolution, okay? And you can have 10 bits or 11 bits, okay? That depends on the ADC. Typically, the values are between 10 and 12 bits. And also you have a voltage reference, okay? So you need to take into account the voltage reference of your ADC, of your data acquisition system, and you divide that by 2, elevated to the n power, that is the number of bits. So based on this information, you will have a step size. That is basically the changes or the discrete changes that we are taking in order to map the continuous signal into a discrete representation. Okay? So for example, for an Arduino, the step size, okay, is of 4.88 millivolts. Okay, that means that the smallest of change of voltage that we can measure is this value, 4.18887 millivolts. Okay, that is the smallest amount of volts that we can measure. And also the Arduino makes this conversion. It takes these changes and translate that to a binary number, okay? So we are computing these changes and transferring to a binary representation, okay? So if we measure a voltage that is 3 times 4.18, well, we can translate that value to this binary number and so on. And that is useful because we can use this conversion that is basically a rule of 3 numbers in order to map this voltage value into a binary representation, and we can make some operations on the data that we are collecting. Okay. And well, in an Arduino, we have 4 connections in which we have analog to digital converters. Okay, they are placed in this region, and we can identify them by the letters A0, A1, A2, and so on. Okay, and well, here I am showing you like the structure of the Arduino in general. And you have different connections. For example, this is the microcontroller. This is a connection to connect Arduino to the computer. You can connect a power supply to the Arduino. You have input terminals that are digital. Also, we have here some pins to produce pulse width modulation signals and so on. You can program the microcontroller using these connections, okay? So there are a lot of elements. You don't need to worry, you don't need to learn them. That's why we have the data sheet. The only thing that I wanted to mention is that, well, remember that the microcontroller is a digital system, okay? So we have thresholds in order to determine what is a low-level signal and what is a high-level digital signal, okay? So we can use this threshold. For example, when the signal is below between 0 and 0.8 volts, we call this a low-level output. When the signal is between 0 and 1.5 volts, we call this a low-level input, okay? We have a threshold here between 3 and 1.5 volts. That means anything, okay? That is not defined. We can have, if you have an input or an output voltage between this region, it is not determined, okay? The Arduino will not classify that, okay? For example, if you have a voltage between 3 volts and 4.2 volts, that means a high level output voltage. And if you have an input that is between 3 volts and 5 volts VCC, it is considered a high level voltage. Okay. So, well, this is basically the TTL level logic levels. Okay, this is a standard. Okay, and Arduino is following that standard to detect input and output levels in a digital signal. And also, well, in order to communicate the information that is gathered by the Arduino to a computer, we need to use a communication protocol. Okay, that is basically the way in which the computers are transferring information. And you can have serial communication. For example, here you need to transfer the bits of information one by one. Okay, or you can use a parallel communication in which you have multiple connections for the different bits that you have, and you can transfer the information in parallel. The disadvantage of the parallel communication is that, well, you occupy more space, but it is more faster. In the serial communication, you are reducing the space, but the transfer of information is lower. The Arduino is, well, can transfer the information from the Arduino to a computer using the serial communication, okay? And the protocol that they are using is the Universal Asynchronous Receiver Transmitter. And it is done by considering these two pins that are connected to the pins of the microcontroller. And well, these pins are connected to this device. That is where we are connecting the Arduino to the computer, okay? And we have two elements. We have a transmitter pin that is transmitting the information, and the other pin is receiving the information that is called RX. And also we have another point that is the receiver pin, okay, in which we are receiving the information transmitted by the computer. Okay. Also, well, I wanted to mention that when you see this symbol that has like this waveform, that basically means that those pins can produce pulse width modulation signals, okay? That is important because you can use these pins to control the speed of the motor by using the driver, okay? So I will leave the presentation until this point, and then I will talk a little bit about what is data analysis.